Okay, we're given this function right here and asked to find any points of inflection, actually just the x-coordinates of the inflection points. So we have to apply the test for concavity, which means finding a second derivative. So here's the first derivative, 22x plus 1 over x. This has nothing to do with the problem, but I will make the observation that when you set it equal to 0 and try to find out what values of x generate a value of 0, there are none because you'd be taking the square root of a negative number. Also, the first derivative is undefined when x equals 0 because you'd be dividing by 0 here, but 0 is not even in the domain of the function. So there are no critical numbers. The second derivative is 22 minus x to the minus 2. There's the formula for the second derivative. To find any potential points of inflection, we want to set the second derivative equal to 0, solve for x. So if I multiply every term by x squared, this is what I get. And solve for x. At this point, I could say x equals plus or minus the square root of 1/22. But minus the square root of 1/22 is not in the domain of the function. So we'll ignore that. And if you wanted to rationalize that value, you could write it like that. Okay, so here's the little number line for the test for concavity. On the number line, we put this hypercritical number, which is when the second derivative equals 0. Radical 22 over 22 is about 0.2. So we want to test numbers on either side of that x number. So if you try f double prime of 0.1, you get 22 minus 1 over 1/10 squared, which is 1/100th, which is 22 minus 100, or negative 78, which is negative. And when the second derivative is negative, that means the original function is concave down. Okay, the way to think about it is the tangent lines are decreasing in slope. I like to just think negative is a frown. That's how I remember it. And to the right of 0.2, like 1, gives us a positive number, so smiley face. The curve is concave up. Since the concavity changes at this point, that is a point of inflection, or the x-coordinate of a point of inflection. If you actually wanted to find the y-coordinate, you'd have to take this number and plug it into the original function to get the y-coordinate. Okay, and so here's what the graph looks like. This is the graph of the original function, and it looks like to the left of this point, the curve is concave downward. Right here, it changes to concave upward. Kind of hard to tell, but that's what's happening. And so here's how you'd specify that in interval notation. Concave down from 0 up to square root of 1 over 22. Concave up from square root of 1/22 to infinity. There you go. Hope that helped. If you have any questions, post a comment.